My name is Ross Centers, and I am the lead for Team Laser, the Colorado School of Mines and the University of Arizona's joint entry in the 2020 Big Idea Challenge. Our entry is a demonstration of laser power beaming for the lunar surface, a technology that will open up the moon's permanently shadowed regions to exploration and to find within them clues about the origin of the solar system and resources to open its frontier for human expansion. 2020 was not a showstopper for us. We began work on rapid prototyping at home, and as safety protocols developed, some of us returned to campus and began building and testing prototypes in the lab. Working with high-powered lasers required additional safety protocols, but through it all, we were able to build a functional prototype and demonstrate its capabilities. The context for our project is in figuring out how to deliver power across extreme terrain on the moon. There is water trapped in certain craters, permanently shadowed regions which haven't seen sunlight for billions of years. Water is essential for life, but also for space transportation. Space travel runs on rocket fuel, and by electrolyzing water into hydrogen and oxygen, we can make a complete, perfect rocket fuel. The tyranny of the rocket equation is that we need exponentially more of it the further we venture from Earth, unless we develop a source of supply using space resources. We will never be an interplanetary species without a supply of water beyond Earth, and these permanently shadowed craters offer the closest supply on our nearest celestial neighbor. To break the tyranny of the rocket equation, we need to explore and develop the moon's water resources to create a gas station in space and a highway to our future in the solar system. The challenge is that where the ice is in permanently shadowed craters, there is no source of energy. Energy is abundant on the crater rims, which receive almost permanent daylight for the same reason that the crater bottoms are dark. The distances between light and dark are on the order of kilometers, but the terrain in between is harsh. The right-hand image shows the South Polar region, and what's important to note is that the vertical relief here is scaled in kilometers. It is much more like the Grand Canyon than Antarctica, and in traversing it, you have to deal with dust that is like microscopic razor blades. Our solution is laser energy transmission. The right image shows a concept of a laser power beam from a sunlit lander into the darkness of a deep crater. A laser transmitter on the rim beaming power to a rover operating in the ice fields below, characterizing them in detail and roaming freely with a mission duration unlimited by battery capacity. The power can be delivered anywhere within range and line of sight instantly, and without mass penalty. Our concept, the Lunar Autonomous Scalable Emitter and Receiver, is a minimum viable prototype intended to pave the way toward this full-scale concept. The mass and power constraints of the Big Idea Challenge drove a creative solution wherein the laser transmitter powers a swarm of minimum mass receivers that are ejected from the lander deck. The transmitter communicates with the scattered receivers, which communicate their charge state, temperature, and location via mesh radio frequency localization. The receivers are covered in photovoltaic panels through which the laser transmitter charges their batteries. Telemetry from the photovoltaic panels also serves as a closed-loop aiming system.
The laser system is a rideshare payload for any CLPS lander. It remains stowed until after touchdown on the lunar surface and can be deployed at any point in the surface mission sequence. Upon deployment, the dust covers eject and the system undergoes an autonomous health checkout, after which the receivers can be ejected. With a fixed aim point and ejection force, the receivers have no need for targeting decisions. There is swarm redundancy in case some of the receivers fall behind a rock or otherwise fail. Once deployed, the receivers form a mesh radio network and communicate with the transmitter. The transmitter then locates each of them in turn and charges their batteries. While the primary objective is to simply demonstrate laser power beaming on the lunar surface, the laser system can also gather science data and assist with other mission elements. The receivers host inertial measurement units and can gather geotechnical data on impact, and further microsensors could be integrated in the future. The laser can be used in other experiments such as heating regolith to evolve volatiles for other remote sensing payloads, and the localization mesh network could also be used to provide position beacons for rover surface localization. We proceeded under a development philosophy of build and test hardware. Iterating under a systems engineering framework, we adjusted scope to build and test the hardware quickly, with what we learned from each iteration feeding into the next. This served us particularly well during the year of COVID, allowing our development to flow around disruptions while building an ever-improving prototype. Our goal was to develop an integrated power beaming demonstration at the highest level of fidelity that we could achieve. Each design iteration focused on establishing core functionality and then extending it towards a flight representative ground demonstration. We used rapid prototyping and integration of off-the-shelf components to build and test a laser transmitter and receiver, working through several iterations before reaching our final demonstration.
Our first hardware iteration demonstrated laser power beaming on an optical bench. At the top left is the heart of our power system, a 4-watt fiber-terminated diode laser at 793 nanometers. This is close to the ideal 808 nanometer wavelength for powering gallium arsenide photovoltaics. We chose it because it was available during the supply shocks of March, and it worked well, establishing an early precedent for working with what resources were available in a chaotic time. The laser is about 9 by 9 by 13 millimeters and generates 4 watts of waste heat. Diode lasers are physically rugged, but thermally and electrically sensitive, so it is mounted to an oversized heatsink and powered by a benchtop diode driver to avoid damage. Fiber termination of the laser package was an excellent design choice for us, enabling development of the beam optics, while essentially abstracting the beam generator away from the separate subsystems. In the top middle, you can see the beam delivery fiber termination within an optical cage, illuminating a 50 millimeter collimating lens, and then a laser power meter. In the top right corner, the power meter is replaced by a photovoltaic panel, yielding a basic function sketch for laser power transmission. We used commodity silicon solar modules in these tests and measured DC to DC electrical efficiencies varying from 2% up to 5.6%. The theoretical efficiency of this system is around 9% and is limited in practice by uneven illumination of the cells and by losses in the charge controller. The first quick win of iteration shown here is that we learned that the beam divergence at the fiber was twice what we had expected, and that we would have to redesign the beam optics to use a 75 millimeter collimating optic instead of the 50 millimeter. We made a beam profile using a Raspberry Pi camera with an infrared filter removed, a 3D printed frame to hold it in relation to the calibration card, and software stack that took pictures of several ISO images for the dynamic range needed. At the bottom left, you can see a representative image of the beam, and in the bottom middle shows the beam profile that we generated. The scale is relative intensity, and the intensity ring around the fringe is uncollimated light due to chromatic aberration of the lens. The final result of our beam development is shown in the bottom right, which is a sealed optical tube that expands the 100 micron beam up to 60 millimeters, where it emerges to collimate a 75 millimeter optic. The unit is sealed against dust in an aluminum tube and can be removed from the bench and integrated into the final configuration. Our transmitter structure evolved through 3 iterations of increasing fidelity. The first iteration, that's shown on the left, consists of a laser pointer and a 3D printed fixture that was used to develop the control logic. It was developed during the peak lockdown and used hardware that was laying around. The second iteration, that's shown in the middle, was a 3D printed article to test component fit. The left arm enclosed a volume for the control electronics, and the right arm housed a vertical actuator. The optical path is within the center drum, with the horizontal actuator being within the bottom fork. One flight representative aspect of this design is the zenith-facing top plate, which at the lunar poles can host a radiator shielded from sunlight as well as terrain. Locating heat sources within the arms really simplifies the thermal contact with this radiator. And our final design is shown on the right. The final design was able to use the optics tube that we used for our benchtop development. It used a milled aluminum frame that was supported by lubricant-free PTFE bushings. A non-flight representative stepper motor was used in the right arm as the vertical actuator. It is oversized to provide the sufficient torque needed for the direct drive configuration that we used. A flight hardware article would use low-profile harmonic drive with a clutch for zero power holding. The control electronics are housed in the module off the left arm, the black box that you see in the picture. A Raspberry Pi 3B Plus is used to drive the system, although this would not survive the lunar environment. Surprisingly, though, it did run in vacuum for an hour. The control logic is simple, but could easily be embodied within a radiation-hardened controller. The horizontal actuation is provided by a direct drive stepper motor within the horizontal PTFE thrust bushing. The torque required for this really impacts the size of the system along with the mass. A more compact harmonic drive would dramatically reduce the size of this for the flight article. The laser diode is still externally located, powered from the benchtop electronic stack. A miniaturized DC to DC diode driver would be needed for development of flight hardware. The diode would be mounted on the left arm with the fiber snaking through a hollow bushing into the optics tube. This makes it easy to keep the hot beam generator in thermal contact with the radiator and allows the optics tube to be free of unwanted thermal loads.
The receiver mass is only 84 grams. The Femtosat demonstrator is a standalone, fully functional 3x3x6 centimeters spacecraft designed to provide real-time solar panel charging telemetry along with inertial motion, temperature, and pressure. We developed 2 iterations, employing a 4 solar panel configuration, charging a tiny Arduino electronics stacks, including a charging board, processor, 433 MHz UHF radio, and a sensor board providing full 3-axis accelerometer, gyro, and compass readings, along with temperature and pressure. Special high-sensitivity current sensors are integrated with each solar panel, capable of distinguishing charge levels as low as 5 milliamps. Telemetry for all these elements are provided to a ground station at a 2 Hz rate. The current version of the Femtosat only supports one-way communication with the transmitter, providing low bandwidth telemetry in short bursts to save power. Powering the receiver in the Femtosat full-time is untenable, given the current draw, but windows of powering the receiver could plausibly be enabled by signals provided by the modulation of the power beam itself. The Femtosat could be upgraded to turn on its receiver for short durations, following appropriate power beam signals, enabling a path for two-way communication. This approach can be implemented by only software modifications to the existing Femtosat. We are currently working on improving the robustness of the two-way communication code. The receivers are ejected from the lander deck from a spring power launcher. The cubic geometry provides potential for insulation, and solar arrays on 4 sides allow for laser illumination under most landing orientations. Because the receiver mass is so low, multiple receivers are used for redundancy and to demonstrate power beaming to a swarm. The receiver sensors can provide basic science data on the geotechnical and thermal conditions of their impact site. The platform can scale to accommodate other miniaturized sensors and could serve as a network of localization beacons for surface navigation.
Our demonstrations verify feasibility of 3 core functions of the laser system: power beaming at range, autonomous localization, and receiver deployment. After first demonstrating power beaming on the optic bench, using early results to evolve our optical design and to measure electrical efficiency up to 5.6%, we worked with environmental health and safety to identify an enclosed, access-controlled area where we could test our system at range. The steam tunnels under the Colorado School of Mines turned out to be the solution, and we demonstrated power beaming there with a low beam divergence on a 30-meter stretch of steam tunnels. Our design for autonomous localization and charging consisted of a 2-level localization, with a search volume defined by radio triangulation, which is then raster scanned by the laser transmitter to find and lock onto the receiver. We tested Decawave RF localization development boards, which provide a mesh localization grid with 10-centimeter accuracy at ranges up to several meters. These chips could be integrated into a Femtosat platform to provide coarse localization of the receivers. We demonstrated fine localization and target lock by raster scanning the laser and identifying illumination with photovoltaic telemetry. The largest risk for receiver deployment is surviving impact on the regolith. We modeled the ejection and calculated representative velocities, which we subjected the receiver to in the Colorado School of Mines regolith simulant testbed. We also subjected photovoltaic modules to regolith testing and measured their output. A core goal was to demonstrate power beaming at as long a range as possible. This is the labyrinthine approach to a 30-meter stretch of steam tunnel in which we found the longest enclosed stretch of space on campus to demonstrate our Class 4 laser system. Despite being 100 degrees in here, it's the stuff of engineering cinematography. The test was conducted with the sealed optics tube developed on the bench. You can see the laser fiber trailing in from the rear. This tube was later integrated into the complete transmitter. Now we walk down the far end of the tunnel to set up the receiver. If you're wondering, the tunnel is sloped because it used to be a swimming pool, campus archaeology. We'll see Josh setting up the experiment and note that he's always wearing his laser goggles as well as his COVID PPE. You'll see that at 30 meters, the receiver is brightly illuminated by the laser beam, with a crisp beam profile and little spillover. Walking back along the tunnel gives a sense of scale. And we're out. Hot in there. While we were setting up, we measured the beam profile along the tunnel's length and found that the beam divergence was minimal, with the spot size increasing by only a few millimeters over the measured range. The quality of collimation was better than we expected and indicates that the useful range of this power beaming system should be substantially longer than 30 meters.
We tested the power beaming system at very short range under vacuum at the Center for Space Resources Lab at Mines. The transmitter and receiver were placed as shown on the right, and the chamber was brought down to 0.4 torr. The atmosphere was not cryogenic, however. The receiver functioned well and charged normally. The receiver temperature reached 48 degrees Celsius during an hour-long test, and besides some adhesive melting behind the panel, no damage occurred. The Raspberry Pi 3 on the transmitter reached a toasty 89 degrees Celsius in a highly throttled state, which was able to still process telemetry as normal. We did use a soldering wick to provide thermal contact between the Pi's heatsink and the transmitter frame. As these CPUs normally run hot in the atmosphere, we were quite pleased with these results under vacuum. Autonomous localization and charging is intended to take place in two phases. In the first phase, RF localization provides a rough search volume for the follow-on raster scanning search. COTS localization chipsets made by companies such as Decawave can provide a localization mesh with accuracies of 10 centimeters over a 30-meter range. All this involves randomly scattered tags that would be placed in receivers and a base station anchor system. The raster scanning process, as shown in this test in the steam tunnel under Mines, is focusing on proving the raster scanning over a 2-meter area. The transmitter slews to the bottom corner and slowly moves left and right, looking for the receiver. The receiver is sending a constant stream of telemetry back to the transmitter. The transmitter is looking for a power spike above a certain threshold for it to know that the receiver is fully illuminated. The coolest part of the raster scanning process is when the transmitter locks on, such as right here. You notice that the transmitter immediately stops. The receiver is still sending transmissions of its voltages, current, and battery status.
Receiver ejection is inspired by Peapod ejectors used for CubeSats. You can see on the top of our lander, we have our transmitter, and then we have our CubeSat ejector, which is our Peapod. In that Peapod, which is that little square on the right of the lander, you can hold up to 4 of these femtosats. All of these items, the transmitter, ejector, and the lander, are on a 1-to-1 scale in this animation, and this animation also has realistic lunar gravity, and the trajectories and times that these femtos take in those trajectories are all what we would expect to see on the lunar surface. After modeling the trajectories, we recreated them in the regolith testbed. We kept the ejection force and angle the same as what we're expecting to experience on the lunar surface. The Earth's gravity just made that parabola a little bit smaller. We ended up rigging together a Pilates band and a ramp made from 2x4s, which you can see on the left side of the slide, to create our stationary scientific slingshot. We marked how far we had to pull back the Pilates band to launch the femto exactly where we wanted it and have the cameras ready at those angles. So after 2 hours of testing, we took apart the femtosat to examine the regolith infiltration. And you can see we weren't, in this video on the right, we weren't the gentlest with the femtosat. So it survived a number of drop tests and a number of ejection tests where it's rolling, tumbling, and hitting the lunar test bed. And so we saw minimal regolith infiltration and minimal cosmetic damages and no loss of function.
One of the design risks for our concept is the effect of dust adhering on the solar panels as the receiver tumbles through the regolith. We measured the effect of dust on similar solar panels by tipping them into regolith simulant and then bringing the panels to upright again, mimicking the effect of a tumbling receiver panel that ends up oriented toward the lander. These tests provide initial data, which is encouraging, but should be considered low fidelity because the plastic coating on consumer photovoltaics is not similar to those on space cells, and because the test was not conducted under lunar electrostatic conditions. You can see on the left that different levels of dust remained adhered to each of the two tests, with LHS-1 simulant and JSC-1A. On the right, panel output is plotted as a function of laser input power. Below a threshold intensity, panel output is reduced roughly proportionally to the amount of dust adhered to the panel. Above this level, however, the dust-covered panels produced as much power as the control. While we're unsure what causes this behavior, the experiment indicates that we might be able to compensate for the effects of moderate dust adhesion to the receiver by increasing the laser intensity, something that is not possible with solar photovoltaics. Our team's development of the Lunar Autonomous Scalable Receiver and Emitter System was the result of the hard work and cooperation of over a dozen teammates at the Colorado School of Mines and the University of Arizona. We worked together through unforeseeable circumstances to build and test an integrated prototype of a laser power beaming system that can be developed toward a flight article for Eclipse lander, and conducted tests that retired several key risks of the system. Our 30-meter power beaming demonstration proved that the optical system has the range needed to power receivers at a substantial distance from the lander. The performance exceeded the length of our longest available testing environment. Testing in atmosphere, in this case, was a harder environment than in vacuum. We demonstrated autonomous localization and charging using closed-loop beam control based on receiver telemetry. Taking advantage of a cooperative receiver makes for a much simpler and more robust targeting system than solutions for adversarial problems. Further development can make our approach faster and more precise at longer ranges. Our receiver survived vacuum and impact testing and was not adversely affected by lunar simulant dust. Further demonstrating useful functionality in an 84-gram payload offers an exciting path forward for miniaturized planetary science experiments. Current funding opportunities encourage scaling up laser power beaming systems to power rovers operating in the ice fields of permanently shadowed craters. On the right is a rendering of a laser-powered rover exploring ice deep in a polar crater, being powered by the laser transmitter we saw at the beginning of this presentation. NASA has identified power beaming in the 100 watt to 1 kilowatt range at distances of at least a kilometer as a baseline capability and has solicited research and development to meet it. The Colorado School of Mines and the University of Arizona have brought on industry partners for a proposal to the Lunar Surface Technology Research Solicitation for a high-intensity, long-range laser power beaming system which these images represent. This breakthrough technology would allow high-powered rover operations anywhere within line of sight of an energy-rich transmitting station. NASA's Small Business Innovation Research Program also solicits small businesses to develop a laser power beaming system in the 100 watt to 1 kilowatt range. A new small business spinning off from this Big Idea Challenge project could be powering rovers in a small permanently shadowed region in 3 years. And lastly, NASA's Watts on the Moon Challenge offers prizes for power transmission systems of similar scope. Keep an eye out for laser power beaming entries. All of these programs, alongside the Big Idea Challenge, offer crucial early government support for a technology that has the potential to revolutionize lunar exploration and offer humanity a foothold beyond Earth from which to explore and expand throughout the solar system. NASA funding supporting technology development and illuminating the value of that technology can start the flywheel of commercialization of lunar development. The history of American industrial development shows that when government provides early support with transportation and power, industrial economies can take root in new frontiers. We are keenly aware that, no matter what develops on the lunar surface in this new era, it will all require power. Thanks to everyone on the team for your perseverance and hard work, and to our faculty advisors, Dr. George Sowers at Mines and Dr. Jahan Tenga at Arizona, and to the Big Idea Challenge for giving us the opportunity to conduct this work.